Hi, Martin. Can you hear us?
Yes, I can hear you. Likewise.
Okay, super. Yeah, floor is yours, and you can start presenting. Apologies, everyone. So we have some technical challenges. So Martin is here. Martin, warm welcome. Please go ahead and present. Thank you.
Yes. Hi. So today's topic is Oracle Performance. Oracle Performance for the uncertain. It's just a joking title. I'm sure you know perfectly what you do. I want to show you some details about Oracle integration into Linux today. My name is Martin Klier. I'm a solution architect and database expert. And my focus is on performance tuning, high availability systems, cluster application. My background is being a Linux admin. So I never was a developer. So I always spent my time with integration work and was involved with databases in 2003. In fact, starting with real application clusters, having no other database experience before, in search of having a very reliable cluster. And in 2003, 10G real application cluster wasn't exactly fun. So I learned a lot about this. In 2016, I was made an Oracle ACE director. And yeah, I love to speak at international conferences. And so speaking for India finally is a new challenge. I never had the chance to visit your amazing country. So having remote sessions and trying to talk about topics of interest for international audience in India is a good and interesting thing for me. My company, Performing Databases, we are 3 consultants. We are 3 experts for database technology. Our focus is concepts and project competence for our customers. We do architecture and system planning, the connected licensing, and of course, implementation and troubleshooting for all things databases. The address is included. I will also share the slides after the presentation on our website and with the All India user group. If you would like to visit our pages, it's performing-databases.com. Just drop by and you will find lots of old talks and informations about Oracle. Yeah, that's an execution plan. We will not go too deep into details, but the plan should be, or the plan is to understand what happens there, but on a very, 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 very low level. So we will start with the operating system, with very basic things to know. First thing, when we talk about performance, I want you to realize that you can measure performance in 2 ways. You can measure latency and you can measure throughput. And whenever you talk about performance and degradations of performance, I will ask you to measure both at the same time. That's a scenario. It's a street. It's a road. Everybody should know that picture. This is an example for high throughput but high latency. So when you look at the cars, the road is quite crowded. It's jammed, and the one guy on the left with a red arrow, he will not get from left to right in the fastest possible time. So the latency for getting from here to there is quite high. But you have to keep in mind that the state or the company who built the street, the road, was not interested in building a racetrack. They were interested to transport people from here to there, and so there's a collision of interests. This one guy wants to go from A to B as fast as possible, but the road is used best when many cars use it, not to an extent of jam, but a given number of cars is necessary to use the road to its best use. But the guy who wants to go to work as fast as possible may not honor that. Otherwise, at night or off-peak hours, the throughput is low, so there are not many cars going from A to B, but the one guy who tries to do it as fast as possible is successful. And when you think about your disk storage or your CPU, you can have quite similar effects. Let's talk about the background. We have to talk about the units of work. Whenever we want to measure performance, we have to measure the work we do and measure how much time it takes to do it. So the throughput, for example, is work per time. You all know the units, you know the megabytes per second, throughput of a SAN. Floating point operations per second, that's the power of a CPU. Or, as in the previous example, cars per hour. When we measure latency, it's the other way around. We say it's time per work. So it's a time per work unit. So how many milliseconds does it take to perform a read I/O? How much time does it take to execute an instruction on a CPU? Or how many minutes are necessary for your commute? That's latency. And as I told you, it's a collision of interests, and the function is exactly the other way around. When I have high throughput, it's very likely that latency is high. And if I have low throughput, the chance is high that latency is low as well. So if you optimize for latency, you have to look that nobody jams you with high throughput demands. And if you want to have high throughput, be aware that you affect people expecting low latency. Another theory part of this talk is queuing theory. Queuing theory is a little bit like a religion because it tries to explain things you cannot prove, but it's a very good picture to explain things that happen in all systems. So when you look at the very basic queuing diagram, the basic queuing diagram has two axes. One is the response time. Time usually goes for the x-axis, but for today, the response time is a dependent value. So the independent value going to the right is the load. So everything we see here in the graph is related to the current load situation. And when we look into a very common system, the curve will look like this. This means that the more the load grows, the more the response time will increase, meaning latency. So on the left-hand side, you can see a very constant and level response time. The response time is never zero because everything you do is, for example, computing or whatever, it will always take a given amount of time. But when load increases, there's a point where the load causes the response time to explode. Depending on what you are measuring CPU, measuring disks, measuring whatever, it may be at a different point, and the curve may look different, but this elbow in the curve will always be there. So when we look how the times are created, as I told you, it will always take time to do something. So this is called the service time. But when you look at the CPU, it takes some time to calculate 5 plus 5. It will always take a given service time. But if you want to calculate 5 plus 5 on a CPU, but cannot because another guy is jamming it, then you have to queue. And this queuing time is non-productive time, but it's lost for your application. And it's poison for latency-sensitive applications if you have queuing time. So whenever you want to calculate 5 plus 5, look at how big the load on the CPU is at the moment, and you can guess how long it will take until you get your return. The math is simple. Response time is queuing time plus service time. And it's true for every point on the curve. And depending on the load situation on the system, you can, if you know the curve, depending on the load situation, you can guess how long the response time will be. The curve is something you have to measure or have to get from your system vendor. Another thing, this elbow, it should be the sizing target. There's no use to go for a fully loaded CPU, for example, because a fully loaded CPU will not give you instant response times. So when you look at your CPU, you have to put the maximum for your estimated load to a point that's not right of the elbow. And the hard part is to find out what should we consider as being the elbow. The elbow for this definition is where a line touching the curve and going through the 0 point of the graph. Where the line touching, going through the 0 point of the graph will touch the curve. This is considered being the elbow. So your load should never be right on this dotted line, never be right of this dotted line, even though the CPU can handle it. But if you want to have constant response times, your load has to stay on the left. That's a very important part. And people have the tendency to forget that when they buy systems, or especially when they do virtual environments. By purchasing a CPU with 20 cores, you purchase 20. And there's no point in overcommitting it with virtual environments. The load will always be limited by the physics. And your physics sizing should come from this graph. Yes, left is the happy part, right is the bad part. Whenever you do performance analysis on systems, it doesn't matter if it's on the cloud or is it virtual or is it on premises. You need a tool that keeps statistics on operating system level. And for me, it worked very well to go for NMON. And a very handy tool for it, it's NMON chart. NMON is Nigel's monitor. It was developed for the AIX operating system initially, and is part of the IBM Power architecture concept. But in the meantime, ports for NMON are available for all platforms. They are especially useful for Linux, and all we do today is related to Linux. NMON creates flat files tracking operating system metrics. And if you want to see them in a visualized manner, you can use NMON chart on your workstation. Just download the flat files from the server to your workstation, use NMON chart there, or you can also have NMON chart on the server if you like, and generate your charts there. The output will be an interactive HTML file using the Google virtualization libraries. The syntax is not that complicated. You have mostly to tell with the -s parameter what the sample interval should be, and c is the duration, how long you want to sample. So in my case, it's 120 minutes. So you have to restart NMON after 120 minutes to have continuous samples. And if you want to create a chart afterwards, you can do it whenever you want. You have to give NMON chart the input file, it's the flat file, and the HTML file, and that should be the output. It's as easy as it is. And what you can do with it, you can see in the background. We will go through some of the graphs in the later progress of the meeting. We have to talk about resources as well when we talk about performance. Resources, for example, are CPUs, memory, network, and disk. Since we don't have more time than an hour today, we only will cover CPU and RAM for now. So let's start with the core of our servers, with the core of our computers. The processing unit. When you look into CPU consumption and want to see how much load we have on a system, there's a good command that's called time. In my case, I do a very simple thing. I unzip an Oracle setup, an Oracle install package, and shove it over to dev null. So I unzip it and drop it. So it's mostly CPU consumption what I do. It's unzipping a file. The time we feel it takes is the real time value returned by time. It's the wall clock time. The time in user land spent for computing C processes and whatever, including all the time you waste with your code, it's included in user time. And if we have to do syscalls in the kernel space, that's in sys. So it includes all the I/O stuff and system-specific calls. A very common tool as well is top. Top will give you a very good picture of the overall situation. In top, you can see mostly the same values. You can see the time spent in userland process. You can spend the time you can see the time spent for kernel times, and you can see the time spent for I/O waits. That's a very basic and necessary information if you want to find out bottlenecks. You also can see that my process here is spending 100% of one core. So if we have a threaded architecture, for example, a Java virtual machine, this can go way beyond 100%. So if it's spanning multiple threads, you can see here values of 200, 300, 400%. So it's using more cores. This is the history of the same values displayed in nmon. So it's a history over 24 hours. The green part is idle. So the green is where you can go if you need power. The blue stuff is consumption of your code. Red is the unavailable kernel syscalls. And orange is the wait time. So how much wait for CPU for I/O calls to occur. And for a history perspective, from a history perspective, it's necessary because people will complain afterwards. So when they complain about 11 o'clock, then you can see that CPU spent was quite high. So you can investigate in direction of CPU consumption at the time shortly before 11 o'clock. CPU load curves are dangerous and false friends. So this is how we would draw a simplified CPU load diagram. Just have to make sure that you still can hear me. Yes, you can. This is how we usually draw CPU diagrams. So when we have another load to add, so I want to add another workload since my CPU is at 50% and we have 100% possible to consume on my CPU, then of course I could add my load and it would look like this. Yeah, sounds reasonable, but it's not exactly right because CPUs don't work like a bucket. You cannot fill in 50% of water and then fill up another 50%. That's too easy. CPUs work with time slots. So in our case, program number 1 starts, and at some point after execution, it has to preempt. It gets kicked off the timer, the scheduler, and it has to preempt for process number 2. And at some point, process number 2 has to preempt for process number 3. And at some point, if it's lucky, process 1 is brought back on CPU. And then in this second blue box, process number 1 makes a serious mistake. It requests an I/O. So it's kicked off the CPU time schedule again. Process number 2 can take over. And in the meantime, we hope that process number 1's I/O call gets processed by the I/O subsystem. And if it is done in time and there's another free schedule on the CPU timeline, process number 1 comes back on CPU and can do whatever it needs to. That's a very simplified picture from Wikipedia. Let's transform it to our situation. So this is how this black and wrong curve would look like in reality. It consists of lots of small blocks, always using 100% of CPU and then nothing, 100% nothing, 100% nothing. And if the times of using 100% and nothing are equal, it's 50% in average. If the load goes lower, the distance between the bars gets bigger. If the peaks get higher, the bars get closer together. So if I want to add more load, I fill in the gaps. In this case, it doesn't look dangerous. Most times it will not be dangerous, but it depends what your expectations for latency are. So if your expectation for latency is smaller than 1 red bar, you can face a delay until you can be scheduled on the CPU. Let me clarify this with a very overdone example. So when we are about CPU latency and we have one big operation running, this is the 3rd red bar in my graph, and I want to insert my load at the beginning, I have queuing time on the CPU. I have to wait until there's an empty time slot on the CPU. And this is the death for your latency optimization, because you cannot calculate. Yes, and in average, it's 50% CPU load. So be careful with 50% and percent mentions of the CPU. If they sample the load in bigger intervals, the load numbers of a CPU are very likely to be false friends. And to make things worse, some bright guy invented hyperthreading. Hyperthreading is nothing but institutionalized overcommitment. So the basic concept is that emptying the input and output queues of the CPU can cause empty CPU cycles. So what they tried to say, whenever the CPU can intake data, there should be a queue having data ready. For throughput optimization, that's the optimal way to go. So for throughput optimization, hyperthreading system will have around about 125% of the power of a non-hyperthreading system. But if you want to have latency optimization, if you want to optimize for optimal responsiveness of the system, you're calculating the operation in A. You do not care for B. B is a noisy neighbor, is the guy from next door who disturbs you. And if the constellation is right, you have to wait for the calculation of B before A can be calculated. And if A and B have the equal execution time, then you end up with double execution time as you had without hyperthreading. And you have to really think about that. If you have hyperthreading and cannot control the second input channel, then somebody else might calculate when you want to, and your response times explode. So be careful about that. If you want to see details about the hyperthreading problem and the general problem of virtual environments committing and overcommitting CPUs, use this link. Just look in Google for Martin Clear Oracle on VMware. You will find the slides for it everywhere. Another false friend is the Linux load average. The Linux load average has 3 digits. It has 3 numbers. So you see that my GZIP consumed 97% of CPU, so roughly 100. And you can see in the time plus column that it was running for 1 minute, a little bit more. But the load average, the minute average, the first thing is only 0.66, only 2/3 of full load. So that's nasty. Where does it come from? Not only top can display your load average, uptime does the same. So for the sake of having short outputs, I used uptime for the next situation. The load average for 1 minute was 1.01. The load average for 5 minutes was 0.6, and the load average for 15 minutes was 0.3. So what does it mean? I would expect to say, okay, a load average of 1 means that in the last minute I had 100% of CPU consumption. In the slide before, I showed you that this is not the case. So where does the difference come from? Again, it's lies. Brendan Gregg is a bright guy. He made an investigation on this. And you can see he got to roughly the same value as I did. So when you look at the left red vertical line, after a 1 minute average, he came to 0.62. So we are quite close. So what's the problem? The problem is that those lines you can see are not lines, they are stairs. So they are sampling again. They are sampling again, not continuously. They are also again smaller averages of smaller intervals, and it's summing up problems. And summing up problems and accumulating errors in calculations will break your calculation on the long term. And when you see the next slide, you can see it's not only using CPU, it's also using it's also taking time into account that comes from accessing disks and accessing other values like RAM. And it contains running and queued processes. This is the basic problem there, that a queued process is still load on the system. So for example, if you wait for an IO and maybe for swapping or other things, it is still load on the system, but it's more than using one CPU. It's just having load on the system, but not CPU. It's also going for disk. Ja, ich bin gerade in einem Telefoncall. Kann ich die einfach hochklappen?
Nee, das geht nicht.
Ja, was soll ich denn jetzt machen?
Ja, einfach von da oben darf normal niemand parken.
Okay, sorry guys, I have to move a bit. Just stay on the line. So sorry for the interruption. Okay, so and this behavior in Linux was there for forever. So in 1993, the kernel code was committed, and you still have the same functionality in the concept. A good thing, if you want to reproduce this at home, is do an NFS mount, do an NFS call, and this NFS call can easily be stalled by interrupting the network connection. And by doing this, you can see that the load average will steadily increase and increase and increase and increase, and CPU load is 0 because the thread trying to do this NFS call cannot run again because the I/O is hanging, and thus is not using CPU. So it's an easy way to see that with a system with even only one core, you can easily create a load average of 4 or 5. It's not a problem at all. If you want to look into the load picture, or your CPU, or you want to complete your CPU picture, use 3 more tools. Use MPStat, use TOP, use VMstat, and use IOstat. They will give you all different aspects of how your CPU is currently loaded and why it is loaded. So getting a CPU picture is not simple, but it's doable. So far for CPU. So let's go for RAM now. RAM in Linux is a little bit trickier than CPU is. So whenever you run your top and switch it to switch memory columns on, you will see that there are virtual memories, reserved memories, shared memories. But when you add them up, if you build a summary of them, a sum of them, you will get values that are way beyond the amount of RAM that was built into your server. So there has to be something about it. And the answer to this question is the virtual memory management of your Linux kernel. Linux is working with virtual paging. So imagine a process with 16 pages of memory. That's the field on the left. And if you fork a new process, you will not allocate new memory. You will just add more pointers. So now you have another process with also having 16 pages, but in this case, it's only virtual pages. In fact, it's 0. But the process thinks it's 16. And so is the virtual memory size calculated. You just add the 16 and the 16 of the next process, and it has nothing to do with reality. It's just virtual. But when your process starts executing and starts changing pages, and pages get different from the initial process, then they will be materialized as own pages, as pages on their own, with and the pointer will be disconnected. So during execution time, it's likely that your processes will get larger and larger, in fact. That's a very complex topic, and I only explained a very dense and a rough picture of it. So if you want to see details, please read for Linux demand paging. That's the technology that's behind it. And it's a very interesting thing to understand how your Linux machines work. And when you look into your Anmon charts, you get a statistics about forking and execution system calls. It's how often and when processes were generated. So when you run into memory peaks, you also have to look when the page was created and when the process was forked, and this is always closely related. So when we measure RAM usage, it can be virtual memory size. So the virtual memory size of one process is all memory accessible for this process. From the perspective of this process, that's correct. But if you add up all virtual memory sizes, it has to lead to problems, as I showed you before. Another problem is that virtual memory size also includes access to shared memory segments. For example, shared libraries or shared memory like in Oracle SGA. And this shared memory can lead to exceedingly high values for virtual memory because it's counted double and triple and quadruples. The proportional set size tries to access this problem. The proportional set size says it's the private memory of this process plus its proportion of shared memory. Yeah. All processes that have access to any kind of shared memory are put into that equation. This means that you go for a shared memory segment, and no matter if you use lots of it or only a little, you will be treated equally with PSS. This means crap. For practical use, it's crap. The resident set size. That sounds good, because resident memory is what I want. It's not shared memory, it's resident, and it's not virtual. So it's really resident memory, but it includes shared libraries, and it does not take swap into account. So whenever you look into high memory consumption, it's a likelihood there that swapping is an issue. You can exclude that, you can rule that out, but usually if you have memory problems, you still want to see people who are swapped. So the resident set size is also not what you want. So what you like is the USS. It's the unique set size. It's the amount of memory which is guaranteed to be private. It includes swap, and it's not shared libraries, and it's not shared memory areas like SJ. That's my friend. But there's a downside on it. The downside is that this value cannot be extracted by PS. So your very common process analysis tool PS is not suitable for giving these values. You need SMEM. SMEM is an open source package, but it's not included in the major Linux distributions. But USS is the real memory this process consumes. And it's the only way, for example, speaking Oracle now, is to find out how much memory your session processes, your server processes really use. If you want to size your system properly, you have to know how much memory have I to give the system on top of the SGA. And this is the only way you can do that in a reliable manner. And if you look on the right-hand side, look at the difference between RSS and USS and the difference between USS and PSS. So exaggerating memory estimations is a very common problem. And of course, just because it's not part of a process, you will still need the shared memory parts. And for shared memory, it's easier. You have IPCS as a command. And with IPCS -m --human, you get the perfect picture of where our shared memory goes to. And the size is what you want to see. Guess which one is our SGA? Yes, it's the second from top. Do you know why one of these shared memory segments does have a key? The key is the way how Oracle knows which shared memory segment to access when you start SQL Plus /sysdba, when you start a bequeath process. This small 16K shared memory area is not the SGA, but it's a very important memory area where all the access regulation concept of Oracle is done. And still, the question is open. If I do SQL Plus /sysdba, where does Oracle know from which shared memory segment to access? It's easy. The key is the hash value of your SID. So the session identifier, the SID, gets hashed and gets the key of the first memory segment of your instance. So whenever you set Oracle SID equals mydb, then it will use the hash value of this SID to search for a shared memory segment with having a key of this hash value and try to authenticate you against this one. That's the way it works. And everything else is pointers from there. Yeah, memory usage depends on the system. If you have an application server, it's much more interesting. If you have a steadily running Oracle database server, the history in Anmon chart is only of limited use. So finally, we have to go a little bit more into Oracle. Oracle can be a monster, but Oracle relies on some very simple basic concepts and on many complex things in detail. So let's start with one of the detailed concepts. It's a wait event. A wait event, again, is a tool. A wait event provides data for analysis of delay. And a wait event is an ingenious concept done by the Oracle engineers. And I want to show you one very specific wait event that's a good example for how it works. I will show you a mutex wait. A mutex wait for a library cache object. Library cache, most of you will know that, is used for parsing or storing results of parsed SQL. So whenever we have a library, we create a library cache object after a parsing, it has a heap on the library cache. It's the cursor heap. And the first addresses in that heap are pointers to a mutex. So whenever process number 1 does an access on the heap, it has always to go through the mutex. And the operating system below knows that a mutex is like a lock. It's a mutual exclusion. It locks the cursor heap for access from others. Process number 1 has no limitations and no degradations in performance by blocking the mutex, because it has to access the memory pages anyway. And by accessing this very memory page, it locks the mutex automatically. It only takes one CPU cycle. More interesting is the second process. If the second process tries to access the cursor heap 0 of our library cache object, it has to spin because it does an access on the mutex. The mutex is blocked, so try again. Mutex is blocked, try again, try again, try again, try again, try again. And this spinning costs CPU. It's not as much CPU as it uses for a lock, for a software implemented component, since mutexes on most CPU architectures like PCs and similar concepts are done in hardware. So the CPU has a mnemonics function for a mutex, and it's only one CPU cycle to check it. But if we do it frequently, it still consumes time and it still consumes CPU. And it's in vain because we know we will not get it. And at some point, the process gives up. And after, for example, it's configurable. It's the spin, the spin count that's responsible for the point when it gives up. And as soon as it gives up, it tells us the wait event. It queues a wait event that's called cursor mutex, S or X or whatever it tried to achieve. Does it try to achieve a shareable mutex? Then it's an S. If it tries to acquire an exclusive lock on the mutex, then it's a mutex X. And this means that you need, for example, 1,200 failed attempts to get the mutex to see a wait event at all. Before the wait event was signaled, it was just CPU load. But after wasting enough of CPU, you get a wait event. That's a limitation of wait events. They are not there from the beginning. You have to try and you have to fail And in the end, you will get a wait event. But if you get it, it's gold, because you know exactly what the problem is, because every wait event has its origin. And for this case, you know exactly that process number 2 suffered from a mutex wait event because it tried to access a cursor heap and could not. And then it's easy, because you know at this time this process tried to do this, and this has to lead to this. At least if you have instrumentation in your code, which I would recommend anytime. So if you have CPU time, we discussed a big deal about CPU time. In AWR, you also have CPU time. Where? Here. The first information about your CPU time is how much CPU time do you have? You have 14 cores. So when you take an AWR report about an hour interval, you have 14 CPU hours of time that makes your 100%. So 1 hour interval, 14 cores makes 14 CPU hours is 100. Yes, we elapsed 60 minutes of wall clock time, and the database had 518 minutes of activity. Yeah, that's more than 60. Yes, because it's more because we had more resources than just a single thread. So the max capacity would have been 840 minutes. We used 518. Again, look at the load profile in AWR. We have 2 CPU seconds per second. That's the first column, first value. 2 CPU seconds per second. This means two CPUs loaded. For if we have 14, 2 of 14 seconds per second means 14%. Now look at the foreground events. Again, there's CPU time, but that's not 14%, that's 23%. Why? We know that 840 minutes would have been 100%. And when you look at the total wait time, 7,290 in the graph above, it's seconds. It's 121 minutes, makes 14%, as we calculated before. But we have a difference here. This graph shows us 23%. Why? Because the database time was only 518 minutes, if you remember. Let's switch back, just to show you again. Here you can see the database time is 580 minutes. All other time of this 840 can be consumed or cannot be consumed, but it's outside the control of the database. So it's just consequent that Oracle does not take the difference into account, because somebody else could have consumed it, and it's not necessarily the case that it's empty. So all values, all the percentages here are related not to the capacity of the server, it's related to the time the database took to calculate. So it's 23%. 23% of 580 minutes of 840 minutes of capacity. How can we cause CPU load? Of course, by doing processing of instructions. Instructions come from parsing, by calculating numbers, also by accessing buffer cache. Buffer cache access is one of the most common CPU eaters in the world. And you will nearly always, when you look into your AWR reports, you will nearly always see a correlation between CPU load and buffer gets. This means that parsing and calculating numbers in practice does not mean the world. Accessing buffer cache is the enemy. And if people are wasting buffer cache access, they are wasting CPU. But per definition, accessing buffer cache is still something useful, because if you go for buffer cache values, you get something in return, and basically this is what you want. So when you look at my list, you could be convinced to say, okay, this means always doing something useful, doing something to the benefit of the user. Yes, but not always. So if something goes wrong, that's the life motto: eat, sleep, and analyze root cases. Somebody would say eat, sleep, go fishing, but no, in this case, it's doing analysis. This is what we do. We are professionals. The most exciting part is always the hunt for the culprit. Look at this. We have a CPU-bound system. We have DB file sequential read. Woo! Why? Let's have a look. The system is CPU and IO bound. So let's go look for buffer gets. Because even DB file sequential reads have to go through the buffer cache. So if we want to find problems, let's go for buffer gets, because they will cause CPU and all CPU and all DB file sequential reads will also cause buffer gets. So we catch both with one approach. So we look into the AWR report, SQL ordered by gets. And we can see a very bad one. Wow, it's doing 17,000 buffer gets. It does 1.7 thousand gets per execution. It's responsible for 89% of the CPU load. That looks promising. You get the CPU ID on the right, and with this we can look into an execution plan. And this is what I promised you initially. This execution plan was extracted by using DBMS Xplan. And in this case, on session level, statistics level was switched to all. Otherwise, you will not get the buffer gets. But if you have it, you have a column of buffer gets on the right. And this number, 613K, is quite close to what we saw in the AWR report, but it will never be equal. It can only get close. So if you want to see and if you want to find what's causing buffer gets, look in the right-hand side column. So 613K is what we have. And there are operations down below there that cause 610K, which is a quite big part of 613, and another one that's causing 595K, which is still a big one of 613K. So let's look in detail what's going on there. We can see account stop key. That's 610. Okay, we can see the filter below. It's 610. So they cannot do much against it, because if a filter or account stop key gets lots of data, they just have to do a lot. So the reason has to be below there. So there, do you see that table access full? It's not the problem. It's only 15K, but we are hunting for the 600. The 600 come from a nested loop. Oh, the nested loop has the same problem. It cannot do something against the amount of data. The amount of data is defined from below. So this is what you have to do. You have to read buffer gets from the bottom. So in my case, you see that last joining this LU thing and the iTuning LU3 index, whatever. This is where the buffer gets come from. So we can look into details. This join of the XPKTU index and the LU table, this seems to be the problem. So we have to find it, and we have no access to the application. We just look into the database, and we can just have information about what the database does. So where do we get more information from? When you look on the left-hand side, you can see the asterisks, the stars, before the row numbers. So in row number 41, there is a star. And the star means that below in the output of DBMS XPlan, you can find a predicate information for this line. So for line number 41 and for line number 36, which are of interest for our discussion, is the predicate that leads to this operation. And that's a very important thing. So you know that scanning for LU SKU ID and for the packing unit ID and for the status and for the packing unit ID again filtering, this is what causes the excess in buffer gets. And this is something you can take in hands and go to your developers and tell them, hey, this thing is bad. And if you're a little bit adventurous, you can try to create a better index for a pattern without telling the developer. But that's up to you. But this is the point where the craftsmen have to come in, and you gave them everything you could do. You could even point them to the line number of their view and tell them, look at this predicate, this is causing the trouble. And yeah, if you are at this point, you're a skilled and good performance analyst limited to a database. So what we did today, we did a little performance theory. I want to take you home. What's latency and what's queuing? We talked about Linux resources, CPU and RAM. Please remember what I told you about the load average. And I showed you how Oracle wait events are generated. Remember that spinning for a resource is expensive. And develop a sense and a joyful feeling for hunting buffer gets. Basically, I would love to welcome you for any event in the world we get in touch for. I'm always traveling. I'm always going for virtual meetings. I would love to shake hands with you whenever this coronavirus stuff is over. And I love making friends all over the world. And maybe someday I manage to go to India. Or you can manage to come to one of the other countries where conferences are held. I say thank you very much. Stay in touch if you like. You have my contact information. That's my email address. That's my URL of my company's website. If you have questions that you don't come up with now in the Q&A session, just text me an email. You will get a response. It will not be on the same day. It maybe will not be in the same week, but you will get a response. And as I said, I'm happy to get in touch. Let me know if I can do something. Yeah, that's the detail for the load average, the source for the load average. It's all in the slides. And I say thank you and looking forward to the Q&A now.
Hey, thank you so much, Martin. Are you able to see the Q&A section from your side?
I'll try. There are 4 questions so far.
Yes, absolutely.
Okay, I will start at the first one. Oh, they are quite close altogether. Basant Kumar asked, what is ideal load average in top output? What means ideal? If you go for optimization of latency, the load average should be close to 0, of course, because if one small operation should be as fast as possible, the likelihood that this happens is higher when the load average is small. But if you want to do lots of throughput and you don't manage to get your load average high, it might be a problem if you cannot get your system to load. So, for example, if you want to load your system properly and you cannot get beyond 0.6 or 1.0 in load average, but you know that you are CPU bound and a little I/O, you should think about parallelization. It's a classic thing how you can get your load average higher. Then we have another question, an anonymous attendee. How we can discover swapping problems, how we can identify zombie processes. Okay, swapping problems are easy to be detected because you can look at the free output in Linux. You can see that swap is busy. Swapping is swapping in and out. All paging activity shown in top is always paging to disk. And swapping problems are detected the same way as RAM shortages are detected, because swapping is the last resort of an operating system to deal with memory problems. It's not always useful to identify who got swapped, because usually the memory pages that got swapped are not the problem, because they are quite inactive pages that can be afforded to get swapped, or the system thinks that they can be afforded to get swapped. But usually that's beyond the problem. Usually you should find out who starts using memory at this point in time and find out why. But the techniques how to do it is something I showed you today. Look in the memory consumption of the processes and in the consumption of your shared memory process of your shared memory segments, and you should find out who's eating memory. And after you know that, you should know why you are swapping. Next question: whether spinning every iteration goes like 4/8/16 wait time. Whether spinning every iteration goes like 4/8/16 wait time. I'm not sure if I get the point. Spinning every iteration goes wait time. No, the wait time. The problem is that you never know how many parallel threads are waiting, and you never know if you get scheduled back for 1 spin or for 200 spins. This is something you don't know, but I'm not sure if I got your questions right. Is there a way to find real-time total CPU of the database? Yes. All you need is to limit your process list to the number of processes your database consists of. Usually, you can do that by filtering by SID. And if you find the list of processes you are looking for, then you can just add up all the CPU consumption. So if you find 200 processes, all containing your SID, and you see that they are using 345% of CPU, then you know that they use 3.5 core. Next question. Filter and execution plan. What does it suggest? In predicate, it says filter is not null. Does split plan in 2 ways, like with null and not null value. Predicate number 36 may be in explain. Yeah, it relates to my example. A filter is a way to get rid of unwanted data. So imagine the execution plan of in a way of a stream. So the data is generated by accessing segments or objects, and then everything is a stream, and the filter picks out stuff that matches its pattern, and anything else gets away. So the filter pushes out things that matches the pattern and does further processing, and anything else goes ahead. Yes, you can say in a way it's splitting the plan. It's like a junction. It's not an effective junction because a filter is a terrible waste of CPU time. But yes, if you have the data by means of buffer streams and did not exclude what you did not want in the in accessing the segment, for example, in an index, then this is the way to go. How can read a trace file for Aura 4036? What is 4036? I have no idea. I'm not sure if it's related to my talk. Is there any chances where SGA pages move to swap paging area? How to deal with such a situation? Because it will degrade performance. Oh yes, Depeche, you're right. You never want SGA pages go to swap. Avoid that at any cost. The first thing I would recommend for everybody who's setting up a database is use huge pages. Usually Linux uses 4K memory pages. For SGA, you typically use vast amounts of memory, sometimes hundreds of gigabytes, maybe a terabyte. And if you have to split that up in 4K pages, it's very inefficient. So you can bring your Linux to use huge pages and use 2 megabyte pages for memory allocation. This has the advantage that memory allocation gets more efficient. So you need less CPU for memory allocation. And to answer your question, huge pages cannot be swapped. If you cannot or do not want to use huge pages, you can also use a parameter log SGA in the database and prevent the database from getting swapped. If you use the log SGA parameter in the database, you have to allow your user with ulimit to lock an unlimited or very large amount of pages against swapping. This is something that has to be granted to you by root. Last question so far, as I can see. Suraf asked, why are any congestion IO issue response time in NFS mount points Hang's query to ASM $ASM disk? Okay, why any congestion IO issue response time in NFS mount points Hang's query to ASM $ASM disk $ASM disk group, etc. views? Whenever we experience unstable NFS mount points, we experience ASM queries hung. Yes, that's quite easy to answer. Congestion on NFS, hanging NFS links is hell on earth. It's something you want to avoid. Yes, I know it happens. To come back to your question, the $ASM views typically read the headers of the disks. So for example, if you use an NFS share as an ASM disk, it's a perfectly supported setup. It needs to extract the header information from the disk. Remember that ASM has no repository. ASM has no registry. ASM can only find out that there is a disk group if it sees a disk of a disk group. This means, consequently, that if you want to know the metadata of a disk group, it has to look into the disk header of the disk group. If this disk header happens to be on a stalled NFS device, the view will hang until the NFS share becomes available again. I hope I could answer that. I can see no more questions. If there are more, please ask. If not, I'm still available.
Yeah, thanks, Martin. After all going through many technical challenges, people are still on the line. So thank you so much. I'm sure you're busy and traveling. So let's see. Okay, so again, you submitted a number of sessions, so definitely we want to see you in next couple of webinars. I'll work with you in terms of timelines and your availability. Accordingly, we will publish our webinars. And also for participants, please thank Martin in a Twitter or LinkedIn or wherever you like. You can see Martin, Twitter handle here in my slide. And also a very important thing is speaker survey. Spend at least 2 minutes to fill the speaker survey and also ask what you want in the comment section, right? Also, for example, if you want to ask any questions to Martin, we will pass it to Martin through that survey. Also, if you attend entire month webinar, so please send us an email to webinar@aiog.org. We are very happy to send you the participation certificate. And let's see who's coming next week. Oh, oh, all challenges to this today. 1 second. It's not going to the next slide. Funny. Okay, here is another option for me to go. Okay. Good. Let me do another way. Okay, I'm directly sharing the website. You can see that the next webinars, and again, we are working on upcoming webinars. So next webinar is coming from Mike Rittich. If you want to understand about upgrade your databases, wondering how you want to upgrade with CDB, if you don't know about auto upgrade, so if you want it's a masterclass. It's a 2-hour session. So please join and mark your calendars, which is on 12th of August, 2 p.m. to 4 p.m. IST Indian time. Also, we have the next session is coming from. Okay, something is wrong. Okay, so here, yeah, the next session is coming from Chris. It's also a masterclass on shareable cursors. So these are the two webinars we are planning. And also you'll see in a couple of days, the next webinars, we already lined up 3 more speakers for this month. So please join our webinars. And with that, thank you so much, Martin. Sorry, I think you had some technical challenges at the initially, but I think you perfectly covered everything what we want, and you answered all the questions. So thank you very much, and we will host you very soon. With that, I'm closing this session. Thank you.
Thank you very much. Goodbye.